Star Wars. That's the most inspiring part. All right. So that was the Cap Space Challenge. Number 3, Carlos. Number 2, what's up? And coming in, top of the leaderboard, Second Lieutenant Ling. Oh, look at the runners up. Somebody's got their space on. Nice. The next and last section for today's lesson is humans in space. So I could have started this whole thing about space with, just talking about galaxies or physics or whatever. And like I said in the beginning, we want to contextualize what happens. So this part is what leads into the next section and next month's. We're going to be a little more structured about doing our activities. So we'll send out a list of what you might want to have for after it, to do the activity after we have our lesson. But I think space is amazing. I love almost every aspect of it, from redshift to black holes to can you just get to space with a balloon, so but what makes it really fun is we have a history with our species in space, and we also have a strong desire to explore, and that's the next real frontier is space or the bottom of the oceans. But it's more difficult to live at the bottom of the ocean than it is to live on Mars. So all right, so the first guy to step outside of the spaceship was Alexei Leonov in 1965. So you can think this is already a couple years after we've actually had people in orbit. So it took quite a bit of time before they're confident and comfortable building a suit that would protect someone well enough to exit the vehicle. And if you go back and read history of his flight, it's quite harrowing, but he did survive. There's a big problem about staying alive in space. There's no oxygen up there, or very little, depends on where you are, but there's not a lot of gravity. If you're on the moon, there's a little bit of gravity. If you're in outer space, there's no gravity. If you're on Jupiter, you're going to get crushed. So gravity is an issue. Gravity is just a matter of how much mass is next to you. So the size of the planet is going to determine the amount of gravity that you're experiencing. And gravity is the thing we have to fight with a lot of energy. Gravity, in terms of space, represents an energetic distance from pure space. So it's a gravitational potential, sometimes called the gravity well. When we have a spaceship and we go out into outer space, we increase our velocity to escape, to go fast enough, so what we call escape velocity. That velocity is different for however size the planet is, or however size the star is that you're trying to get away from. But once you get to escape velocity, in terms of you're in outer space, free of the major gravitational effects of other planetoids or stars, that's like the 0 point. Everything else is falling down towards something that's got a lot of gravity. And the ultimate of that, of course, is a black hole. So gravity is the thing that we fight, and it's just a matter of energetics. So the more junk we can get up into space and leave it there, the less energy we have to do moving it around. But to get it down to a planet is a loss, and a gain in energy. To get it away from a planet is a loss of energy. So gravity is a real thing we have to fight. There's no food up there unless you eat methane and dirt. So there's no atmosphere on the moon. There's no atmosphere in space. There's an atmosphere on Mars, and there used to be quite an atmosphere on Mars, but Mars, because it has less gravity, all the gases escape eventually over millions and millions of years. So, atmosphere problems are dependent on what planetoid you're on or what spaceship you're in. There's not a lot of water. Well, actually there is a lot of water, but it's locked up in ice, in planets, in asteroids and stuff. So you can't just You can't just, it doesn't rain in space, obviously. And then the worst part is that there's no Starbucks up there. So the Apollo program was one of the biggest programs that our country's done. And it was amazing in terms of how much effort, money, and how many amazing things came out of the Apollo program. This video is just phenomenal.
14, 13, 12, 11, 10, 9. We have ignition sequence start. The engines are on. 4, 3, 2, 1, 0.
Sideways shaking was unbelievable. The vibration was so intense you couldn't see the instrument panel.
We have cleared the tower.
I thought we'd had it during launch. I was hoping that Frank Borman didn't have his hand on the abort controller. He said he took his hand off and he'd rather die than make a false abort.
1 minute after liftoff, the Saturn V is already supersonic.
Well, the Saturn V is still the most powerful machine that man has ever devised. 20 tons of fuel a second, 7.5 million pounds of thrust. I think we were all surprised at how strong that thing was. It had had 2 or 3 iffy missions before ours, but it was a piece of cake. It just worked beautifully. Unbelievable.
5 engines in the first stage blast the Saturn V to 7 times the speed of sound.
The second stage cut in. Big bang.
At 40 miles high, it's still
When
accelerating.
you staged, you were throwing forward in the belts and then backward in the belts.
And I thought I was being catapulted through the instrument panel.
All sources show that the stage is burning perfectly.
The third stage fires twice. First, the boost into orbit. The second burn takes the crew of Apollo 8 where no men have ever been.
How cool is that? That never gets old, actually. I could watch those F5 engines light up in slow motion and burn like every morning. But yeah, so the culmination of this huge program was that product, which we sent up many, many times. The first one was, for the landing, was July 16th, 1969. So fantastic program. Then we progressed to putting space stations in orbit. The first space station, Salyut 1, was launched in 1971. So they lived aboard for 23 days and made the first space station, which progressed ever further until we get to the International Space Station. This thing is amazing. It's kind of a strange contraption, yeah. They have to boost it every once in a while. It's in low Earth orbit, and it does actually have a slight drag. So there's enough particles in this low Earth orbit where the space station will slow down slightly. And slowing down, just like the moon speeding up increases its orbit, slowing down decreases the orbit. So every once in a while, and you can look up a video of it online, it's pretty cool. They have a boost burn where they use one of the progress modules and they just fire it up and it speeds the station up just a little bit slowly. And when he does it, there's a cool video of the guy holding an orange sitting there, and then he presses the boost and the orange starts to move backwards, showing that, you know, it's an inertial frame. Now, here's the thing. So we want to explore space. Should we live in space? Is there good things about living in space or bad things about living in space? Should we build a space station? There's a whole bunch of different kinds of things. People have thought about, hey, maybe we should make a geosynchronous station. So that's a station that's far out in space, that's not in low Earth orbit, and you'd be in synchronous orbit around the Earth. You wouldn't have to boost burn. There'd be no drag. You could stay there for a long, long time. Maybe we should build a moon base, but then that's, again, that the gravitational issue comes into play. You have to put things down to the moon and bring them back up into space. Maybe we should make a Mars base. That's what we're going to investigate next month, talking about SpaceX and how they're planning to move the human race to be multiplanetary and colonize Mars. Maybe a solar system station, a deep space station, right? Or a deep solar system station. The funny thing is these ideas were in play way back in the 50s and 60s. I love this one because they built a ring, which is a good idea because it takes care of part of the gravitational problem. But if you notice, the people are standing upright and the desks and stuff are straight up and down. The whole point of the ring is that you'd rotate the ring to make artificial gravity, and everybody would stand on the outside edge and walk perpendicular to that. So it's kind of funny that they built this type of thing. And there's your rocket coming up, and science fiction, but actually getting some parts of it right.
Major Giles.
So let's talk a little bit about, yes.
There's a question in the chat about whether or not we're going to talk about Project Artemis.
Not today, but we can talk about that next month. We're going to get into a lot more detail about the things that are actually happening and the plans of different people that are, I mean, obviously SpaceX is building these gigantic stainless steel rockets so that we can go colonize Mars. So we'll get into those kinds of details next month. So that's the teaser. So let's take a look at this picture. This picture is actually really kind of cool. If you wanted to, I'm going to talk about geosynchronous station. If you wanted to put a geosynchronous station, you'd need to place it right about here. So these colored rings, does anyone know what those are named? You can type that in chat. I bet you know. In fact, I'm sure about half of you know what those are. Well, unfortunately, the answer's already here. These are the Van Allen belts. And we knew they existed from the 50s, but we didn't know exactly why they're there or what they're composed of and why they're so strong. So this red part represents actual particulate accelerated particles from the sun that impact anything that exists in there. So if you park your spacecraft in this red zone, you're actually going to get radiated and pummeled by, you know, electrons traveling near this significant fraction of the speed of light. So you won't survive very well here unless you build a spaceship that's got like 6 inches of lead all the way around it to shield you from that kind of radiation. That's why you'll notice that the space station is in low Earth orbit below even the inner belt. It's at 230 miles. The inner Van Allen belt, which is narrow and around the equator, the magnetic equator, is at about 1,000 to 8,000 miles. So these belts actually protect anything inside of their sphere of influence from incoming radiation. So if particles come in, gamma rays, other things, they tend to get warped into the belt and not come in and disturb Earth. So Earth's magnetic nature, its geodynamo, is actually something that's protecting us all the time from turning into crispy critters. And that's why if you have a spacecraft, you need to park it in places that aren't in the Van Allen belt. So you'll see the GPS satellites are in between the belts. Lots of other things are, you know, so geosynchronous orbit stuff stays outside of the belt. One of the weird things is they finally figured out when they sent these Van Allen probes, NASA sent these up in 2013, I think. So these are actually pretty modern features. They found that the Earth itself, given the magnetic distribution of energy by the Earth's magnetic field and the incoming electrons, lower energy electrons coming in from the sun, interact in this region. So it's just the right distance for the Earth to pull those electrons into a kind of, it's not an orbit, it's actually magnetic. We call it a magnetic orbit, where they stay in this field and they're constantly being pulled by the magnetic field of the Earth, and so they end up circling the Earth. And they emit radio waves which interact with each particle and slowly start to accelerate, give it a little boost each time the particle comes around. So what I mean slowly is that it gets a little bit of acceleration each time it comes around. So in essence, the Earth itself is the largest particle accelerator that we know of. And it's actually accelerating right at these points to relativistic levels electron matter. So you definitely don't want to be around here unless you want to be pummeled by particles. How cool is that? The Earth is the greatest particle accelerator. Then we talk about, what about a moon base? A moon base would be really cool, but it's not going to look like this, because this stuff would all get irradiated. There's no atmosphere to protect it. There's no magnetic field. Every time the sun has a coronal mass ejection, you're going to get pummeled by material that's going to cause you not to be able to exist. A moon base would more likely look like this. Great big shielding for stuff that's kept on the exterior, a couple robots moving around. Everything else is underground, dug in behind a lot of material that shields you from the radiation. Then we get to Mars. People want us to move to Mars. The thing is, right now, if you move to Mars, there's no real atmosphere to protect you. So again, same thing. You could have all these modules you want. You just have to bury them in dirt. So basically, you're going to end up living in a cave. Maybe you want to go somewhere else in the solar system. There's lots of potential. If you think about the size of Earth, there's some moons we could actually build bases on that would have, you know, significant gravity that we could live on. Some of these actually even have atmospheres. Pretty interesting. And then your last bit, maybe you want to design your own habitat for humans in space. Come up with some ideas about where would you build a space station and how would you make it a solution for what's coming to face us in the near future, about needing to be multi-planetary or just spreading out in terms of exploration. And now I'll be free to answer any questions, and then we'll close it out. Ah, good. So you're talking about the, in essence, the aurora borealis and that effect. So yeah, yes. Why we do see the particulate end up wrapping around those. So they don't just orbit; they do come in, and then at the poles you can see the aurora borealis is the impact of that. And then when those particles interact with the atmosphere, it turns into a plasma. So the aurora borealis actually is a plasma sheet that follows those magnetic lines that's pulling in those particles from the Van Allen belt.
Cadet Staff Sergeant Oki, about the Van Allen belts, when so is it that effective than the greenhouse effect? Would you say it has more effective against the the radioactive stuff, or is it less effective than the greenhouse effect or any other effects that has to do with space?
Okay, so the Van Allen belts don't have anything to do with the greenhouse effect, but they do have to do with protecting us from radiation, right? So the biggest thing that we need to be protected from basically is gamma rays. And gamma rays are taken up by the ozone layer and then the upper atmosphere. So our atmosphere itself is protecting us quite effectively from gamma radiation. Gamma radiation is the stuff you don't want to be anywhere near. And in fact, when you fly in an aircraft at 36,000 feet, you're increasing your exposure to that type of radiation by 3 times. But we've seen over the course of human history that pilots don't end up getting more brain cancer than anybody else. And so that level of exposure is acceptable. But once you get outside of the atmosphere, you do need to be shielded. So a spacecraft and an aircraft have 2 different types of structures. A spacecraft is going to have some type of shielding that protects them from gamma radiation. It's sometimes gold foil, lead, it can be a lot of different things. So that is what happens for the atmosphere protecting us from radiation. The Van Allen belts are protecting you from particulate radiation that would come from the sun, from a coronal mass ejection or something like that. And it diverts it away from the main part of the Earth. And yeah, it does bring it into the poles a little bit. And again, then the atmosphere does protect you.
Okay, so does the space shuttles have like a protective type of, like, kind of like a seal or kind of like metal to protect it from the Van Allen stuff?
Right,
I'm
so
kind of curious.
every spacecraft that we've built, apart from the spacecrafts that have gone to the moon, have stayed within the Van Allen belts. So they're not exposed to the same level of radiation.
Okay.
This is Technical Sergeant Parton. I was asking, is it possible to time travel through space?
We are going to get there in this series, and I will leave that as a teaser. That will be brought up in another one of the lessons where we will cover black holes extensively because they're just darn cool.
I was watching Interstellar, like every minute was like 2 years on Earth. That's why I was kind of like wondering, is it possible if we could time travel through space?
The impact that you're talking about is when you start to go faster, your time base changes. So the faster you're moving, irregardless of anything else, your clock is different from someone else's clock. And in fact, your clock tends to be a little slower. So if you do go into space and accelerate yourself up to some significant potential of the speed of light, and then you come back to Earth, everyone else is going to be a little bit older than
you. Second Lieutenant Ling, I have a comment also. I wanted to add upon that, and then I have a question after. So my comment is, there's something called time dilation, which is just the name for that. So the faster you move through time, the slower you'll be moving through space. And so if you were to be moving at the speed of light, I believe, right, like, I don't know, say for instance, there's a planet millions of light years away, and you're to be traveling at the speed of light towards it. It might take you those millions of light or those millions of years to get there, but for you would feel shorter, and then you would also be younger, I believe. That's how it works. And then also my question is the Van Allen belts affected by solar winds in the same way that the magnetosphere is?
So the Van Allen belts form because of entrapping particles into that magnetic structure. And when they did put up those probes, the Van Allen probes, initially they saw a third belt that formed, and a couple weeks after they saw it form, it got blasted by a coronal mass ejection, a solar wind event that just stripped it away and moved into space. So that third belt is, in essence, unstable. Back to your idea of the time dilation, what it is the faster that you move, the time base changes. So it's not that you can move through time any faster or slower, it's that your experience of time changes. So if you accelerate yourself to a significant portion of the speed of light, then your experience of your clock is different from someone who's going much slower than you. And the problem with that is that it takes an infinite amount of energy to accelerate any mass to the speed of light. E equals mc squared, right? You can't actually have mass and be traveling at the speed of light. So that's the conundrum at this point, why we can't get our spaceships to cruise really fast, is it just takes way too much energy. Light itself, photons, they're massless.
Cadet Staff Sergeant Oki again. So what type of What's the most known chemical in the Van Allen thing? Like, is there like hydrogen, like helium or oxygen?
So what we're talking about for the Van Allen belts is you're entrapping electrons, particles,
Oh.
particulate. So
Oh.
it's not atoms.
Oh, okay.
Good. All right. So thank you again, everybody, for attending. We're going to be doing this again. I think we said April 25th. Keep an eye out on your email. And if you have any questions, you have AEOs in your squadrons you should be talking to as well. Hopefully a fair number of them were in this meeting.
Also, so we're gonna, for the next 2 meetings, we're gonna expect that probably either you have materials that we're gonna request for an activity, or you can have the activity afterwards, and we'll want to see the results of that activity. So we'll work out some way of doing that evaluation somehow.